I'd like to give you an idea of the upcoming workshop on predictive complex computational fluid dynamics, which has as its goal nothing short of the demonstration of the full vertically integrated set of disciplines and skills that go into a modern fluid dynamics simulation on a supercomputer. We begin, of course, with the physics, the conservation laws of mass, momentum, energy, atomic species. And then we translate those into mathematical models. Traditionally, this would take the form of partial differential equations, which record the values of these fields at every point in space and time, although they could represent tagged particles as we track their trajectories through the flow domain. Then we have to discretize this system of partial differential equations for the finiteness of the computer. This means that we replace a continuous domain with a finite network of cells or particles, while keeping track of the error involved in reaching any point in the domain from the nearest observer that we track. This could lead to billions of discrete equations, which we then have to solve, and that's where actually my specialty comes in algorithms for the scalable solution of large systems of nonlinear and linear equations. Once we have an algorithm, of course, we have to code it for a massively distributed computer, such as Shaheen in the room down the hall from this office, which, as you know, is a basketball-sized court of processors and a high-performance network that's able to deliver a number between any pair of cores on that huge computer in less than or equal to 3 hops. This is a choreography of space and time that is one of the more rewarding aspects of creative approach to computational fluid dynamics and other such simulations today. Finally, we have to future-proof our codes because architectures are continuously evolving, and we don't want the decisions that we need to make close to the GPUs or the Intel KNLs. We don't want them to affect the way we formulate the equations at the higher level. So this is an interesting software engineering and computer architecture task. And bear in mind that we want these solutions to be predictive. That is to say, we want them to lead experiments in the choice of domain shapes and parameter regimes to do useful things like produce energy in an internal combustion engine or predict the lift of a wing of an aircraft. And for this reason, we have to be able to bound the errors in our simulation, keeping track of the errors at every stage of the vertical hierarchy that I've just described. Computational fluid dynamics began in the 1940s with John von Neumann. In fact, you could say that all of scientific computing is an outgrowth of von Neumann's ambition for being able to understand things like the circulation of the weather or neutron transport. Today, it's both a full employment program and a lifelong career program to track the evolving capabilities of the discipline and the evolving capabilities of the architectures on which we can host it. We have coming here to KAUST leading experts from industry, from academia, from government labs, who are concerned with different levels of this hierarchy, and also with a variety of different applications, such as a colleague from GE Global working on high-performance combustion turbines, or colleagues from Aramco working on oil reservoir simulations. I hope very much that there's some level at which everybody at KAUST will be able to appreciate what's going on in this conference, and I hope very much that you'll be able to join us.